Welcome to Night Chemistry, your midnight laboratory of calm. Before we explore nitrogen, the quiet giant that wraps our planet, let us prepare the body and mind with one simple rhythm. Settling into elemental calm. Guided 4-4-6 breath. Gently close your eyes or soften your gaze. Place one hand over the heartbeat at your center and feel its patient cadence. Now breathe in to a silent count of 4. 1, 2, 3, 4. Hold that breath for 4 more counts, letting the chest remain comfortably full. 1, 2, 3, 4. Release the air in a slow, unbroken stream for 6 counts. 6, 5, 4, 3, 2, 1. Again, breathe in. Imagine cool night air sliding into the lungs. Hold. Sense the hush between heartbeats. Exhale. Picture any fragments of tension drifting away like pale clouds across a dark sky. Repeat this cycle 2 more times at your own pace. Each inhale gathers composure. Each gentle pause offers stillness. Each long exhale clears the mind for discovery. When you feel the rhythm settling itself, allow your breathing to return to its natural flow. Keep that calm 4-4-6 pattern in the background. Steady, effortless, always there if you need it. Element-specific visualization. Now let imagination rise. It is a clear summer night on an open plain. The horizon is wide, dotted with the silhouettes of distant hills. Above, countless stars shine, yet the air feels surprisingly light, almost weightless. That sensation is nitrogen. 78% of every breath. Silent, invisible, essential. Picture the sky as a vast ocean of dark indigo. Within this ocean float soft waves of bluish mist. They undulate slowly, forming gentle swells that lift and fall without sound. These waves are molecules of nitrogen gas, 2 atoms bound by a triple bond so strong that each pair drifts together for years before it changes. They keep the atmosphere calm, taming the fiercer spirits of oxygen and water vapor, cushioning every flash of lightning and every passing meteor. Step into the scene. Feel cool grass beneath bare feet, each blade storing traces of nitrogen drawn from the soil by whisper-thin roots and friendly bacteria. As you breathe, the air enters, passes through warm bronchi, and reaches deep alveoli. Most molecules depart unchanged, giving only their gentle pressure, their quiet volume, their humble contribution to balance. A few leave behind useful gifts: nitric oxide that tells vessels to relax, ammonia that helps kidneys keep blood pure. The rest float onward, patient travelers in an endless cycle. Look to the northern edge of the sky. A faint green ribbon shimmers, an aurora born when solar particles strike nitrogen high above the poles. The color is soft jade, pulsing in slow curtains. Each pulse reminds you that even the quietest element can glow with silent splendor when the universe brushes across it. Feel a mild breeze begin. It carries no scent, no temperature shift, just a subtle cooling whisper. That is liquid nitrogen in memory only, a promise of -196 degrees when released from its steel flask. Here in thought, it is safe and comforting, a reminder of calm potential. The breeze strokes skin and then settles, returning the plain to stillness. In the grass nearby, a firefly rises and flickers yellow-white. Its light is born from luciferin, a molecule whose core contains nitrogen. A second firefly answers, then another, until dozens weave sparkling arcs that mirror the constellations overhead. Nitrogen is in each brief flash, yet never claims attention. It prefers to work unseen, letting other colors take the stage. Bring awareness back to your resting body. Notice how shoulders have loosened. The jaw hangs easy, unclenching by its own accord. Fingers lie soft, neither grasping nor withdrawn. Calves sink into mattress or cushion. The spine finds a neutral curve. Take one more intentional breath. Inhale 4. Collect the quiet might of nitrogen. Hold 4. Feel the hush of triple bonds, steadfast and balanced. Exhale 6. Allow any last chatter to dissolve into the night air. You are ready. The silent giant of the atmosphere waits to share its story, from 18th century discovery to cosmic birth and living cells. Let us begin the journey, carried on a current of calm nitrogen that surrounds, supports, and safeguards every breath. Discovery 1.1. Who discovered nitrogen? Long before the word nitrogen existed, alchemists and natural philosophers had already met the element, though none recognized its face. They noticed that flames died in sealed vessels after the oxygen was consumed, leaving behind a residual air that would not support life. They called it phlogisticated air, burnt air, and sometimes mephitic air. Each name hinted at mystery, never at essence. The first person to isolate this curious residue clearly was a young Scottish physician named Daniel Rutherford. In 1772, within the vaulted lecture rooms of the University of Edinburgh, he designed a simple yet elegant experiment. He placed a mouse inside a closed bell jar until the creature consumed all the oxygen and fainted. Then he burned a candle in the same jar, exhausting any remaining combustible gas. Finally, he introduced a burning phosphorus wire to mop up the last traces of oxygen. What remained was an invisible gas that would not relight a taper and would not sustain life. Rutherford poured that gas through a caustic solution to remove carbon dioxide and found, to his quiet wonder, that the residue persisted. He called it noxious air. Unbeknown to Rutherford, chemists across Europe were inching toward the same discovery. Carl Wilhelm Scheele in Sweden, Joseph Priestley in England, and Henry Cavendish all played with combinations of oxygen, phlogiston theory, and residual gases. Scheele noticed that when he passed air over red-hot charcoal, part of the air vanished into the charcoal, part produced carbon dioxide, and still a stubborn remainder lingered. Priestley recognized that mice could not live in that remainder. Cavendish, ever the precisionist, measured its density with delicacy seldom matched in his age. Yet it was Rutherford's thesis, under the mentorship of the famed Joseph Black, that first framed the residue as a distinct component of common air. Black encouraged him to remove carbon dioxide with alkali solutions, leaving only the inert fraction. In doing so, Rutherford unknowingly captured nearly pure nitrogen. The naming, however, did not come from Rutherford. In 1793, the French chemist Jean-Antoine Chaptal proposed the word nitrogene, meaning niter forming, because the element revealed itself in nitric acid and saltpeter. The French language soon shortened the term to azote, without life, emphasizing its inability to support combustion or breath. English scientists kept Chaptal's Latin root but fused it with a Greek suffix to form the word we now speak softly: nitrogen. Thus the element passed through many hands, each adding clarity. Rutherford isolated, Scheele replicated, Priestley publicized, Cavendish weighed, Chaptal baptized. Together they revealed a vast, silent ocean of gas that had surrounded humankind since the first inhale. Nitrogen stepped from anonymity into identity. 1.2. When nitrogen was discovered. The story stretches across decades, but its decisive window lies between 1772 and 1793. In 1772, Rutherford defended his doctoral thesis, Dissertatio inauguralis de aer fixo dicto aut mephitico, before the faculty in Edinburgh. He demonstrated the existence of a noxious air that would not relight a flame. His apparatus was simple: bell jars, candles, mice, phosphorus, and lime water. The year marked the experimental birth of nitrogen, although Rutherford still described it through the lens of phlogiston theory. Shortly after, in 1775, Priestley and Scheele each published papers describing the residual, non-respiring fraction of air. Though working independently, they confirmed Rutherford's gas was neither carbon dioxide nor oxygen. Their observations spread through coffeehouse conversations and academy letters, stirring curiosity among chemists. The late 1780s brought refinement. Cavendish used eudiometry and gas density measurements to show that the inert gas formed roughly 4/5 of normal air. Meanwhile, Antoine Lavoisier in Paris demolished the phlogiston model and reframed combustion as union with oxygen. He referred to Rutherford's residue as foible air, weak air, necessary to dilute oxygen in the atmosphere. Lavoisier suspected it was an element, but he died at the guillotine before publishing a full account. Finally, in 1793, Chaptal coined nitrogen. In the same decade, the French chemist Claude Louis Berthollet showed that ammonia contained hydrogen and nitrogen in definite proportion. Prussian chemist Martin Klaproth reported rare minerals rich in nitric acid salts, underscoring the breadth of nitrogen compounds in Earth's crust. By the dawn of the 19th century, the term nitrogen had entered lecture halls and textbooks. Thus, over 21 pivotal years, a nameless fraction of air became a named element, recognized, weighed, and given atomic identity. 1.3. Conditions and circumstances of discovery. The discovery unfolded in candle-lit laboratories where glassware clinked on wooden benches. These rooms smelled of burnt phosphorus, damp lime water, and the faint animal musk of experimental mice. Students wore linen waistcoats and carried notebooks stained with ink and grease. They pumped air with leather bellows, sealed jars with beeswax, and cooled vapors against frost-lined windows. Rutherford worked in Edinburgh, a city of stone closes and ocean mists. The Scottish Enlightenment thrummed through its taverns. Philosophers debated moral sense while physicians studied respiration. Joseph Black had previously identified carbon dioxide, fixed air, by distinct limewater tests. He taught Rutherford the value of scrubbing unwanted gases. Under Black's guidance, Rutherford layered processes: animal respiration, combustion, and phosphorus oxidation. Each removed active gases until only the noxious remainder lingered. Elsewhere, Scheele isolated gases in a rustic Swedish pharmacy. He heated saltpeter with acids, capturing fumes in inverted flasks. Priestley tinkered beside a Leeds chapel attic, using the same bell jars that would later birth the concept of oxygen. Cavendish performed meticulous density determinations in an elegant London townhouse, where brass balances stood as steady as library shelves. No one possessed vacuum pumps powerful enough to evacuate a flask completely. Instead, they relied on displacement. A jar inverted over water would slowly fill with carbon dioxide or oxygen, pushing common air downward and leaving mixtures to be tested. Through repeated purging, chemists obtained increasingly pure fractions. Temperature and barometric pressure shifted daily, complicating measurements. Scientists corrected figures with mercury barometers and painstaking long division. Ink froze in winter, candles guttered in drafts. Phosphorus burst into flame if left unwatched. Yet curiosity persevered. Socially, Europe teetered between revolutions. In France, chemical nomenclature became a political act. Lavoisier, Guyton de Morveau, and colleagues forged a systematic naming scheme, assigning each element a derivative root. For nitrogen they proposed azote, lifeless. Chaptal preferred nitrogen, niter-forming, evoking the saltpeter vital to gunpowder, itself indispensable to the revolutionary armies. Language, politics, and science danced together. Across the Channel, British dissenters debated phlogiston even as new evidence undermined it. Priestley clung to the old theory, yet still provided data that would cement nitrogen's place in the periodic landscape. Cavendish, famously taciturn, published sparingly, but his density tables became standard references for decades. Instruments evolved. The pneumatic trough, wood-lined with wax, allowed gases to be collected over water. Later versions used mercury for low solubility setting. Eudiometers measured changes in gas volume after electric sparks or catalytic combustion. These tools, primitive by modern standards, were marvels of ingenuity, coaxing invisible substances into measurable form. By the time Chaptal named nitrogen, laboratories had begun using KIP generators for controlled production of hydrogen and nitrogen oxides, steam-powered pumps to draw partial vacuums, and cold baths of ice salt for condensing vapors. Yet the essence of discovery still lay in observation. Flames failing, mice fainting, lime water clouding, needles on balances tilting by fractions of a grain. From such modest signs arose the recognition of a vast, silent presence. Every breath we take is softened by nitrogen's cushion. Without it, oxygen would blaze unchecked, fires would rage hotter, metals would corrode faster, and living tissues would burn in their own metabolism. Nitrogen, discovered in flickering candlelight, now stands revealed as the quiet giant supporting life's delicate flame. Gentle pause. Take a moment to breathe in through the nose, 4 counts. Hold 4 counts. Breathe out 6 counts. As you exhale, imagine the triple bonds of nitrogen molecules drifting around you, calm and unhurried. Thousands of scientists since Rutherford have relied on that calm to measure, to hypothesize, and to dream. In our next block we will meet nitrogen's properties. The strength of its bonds, the chill of its liquid, and the rings it draws in cosmic clouds. For now, rest in the knowledge that each silent inhale continues the story those early chemists began 250 years ago. Properties and presence. 2.1. Key physical and chemical properties of nitrogen. Take a gentle breath in and feel the air expand within your chest. Nearly 4/5 of that breath is nitrogen, a silent giant made of unassuming diatomic molecules. Each N2 is 2 atoms bound by a triple bond, 3 shared pairs of electrons riveted together with rare strength. The bond's energy rivals that of diamond lattices and tungsten carbide, yet the molecule drifts weightless, clear and calm. Inert temperament. Because the triple bond holds so firmly, N2 behaves almost indifferent toward chemical invitations at ordinary temperatures. Flames, acids, and even liquid bromine scarcely tempt it. This reluctance underpins Earth's safety. Oxygen fuels fires, but nitrogen dilutes the blaze. Without that cushion, a stray spark could turn forests to ash overnight. Phase portrait. Cool the gas to -196 degrees Celsius, and it condenses into liquid nitrogen, a silent, shimmering pool so cold that moisture in the air crystallizes above it like faint white smoke. Dip a rose into the liquid. Petals freeze solid in seconds and shatter with a glassy chime. Warm the pool by a single degree and it boils furiously, expelling vapor in rolling clouds. At -210 degrees Celsius, nitrogen freezes into clear crystals that squeak when scraped. Raise pressure to the realm of gigapascals, and calculations suggest exotic polymeric phases, chains of nitrogen atoms coiling like springs that release more energy per gram than modern explosives when they snap apart. Isotopes and nuclear calm. Most nitrogen is N14, 7 protons and 7 neutrons. A smaller share is N15, 1 extra neutron quietly altering nuclear spin without disturbing chemistry. Scientists track the N15/N14 ratio to map fertilizer runoff, trace protein sources in diet studies, and date ancient glacial ice. Both isotopes are stable. No common radioactive forms drift in the wind, and thus nitrogen carries a nuclear calm that suits living tissue. Allotropes and ions. Unlike carbon with its diamonds and graphene, nitrogen prefers the diatomic form. Yet under thundercloud voltages it forms transient and 3-azide ions, as reactive as startled cats. Lightning strokes split N2, letting atoms unite with oxygen to form nitric oxide. Far above, ultraviolet sunlight converts N2 and O2 into nitric oxide and nitrogen dioxide, launching the daily dance of ozone chemistry. Odor, color, sound. Pure nitrogen has no smell, no color, no flavor. It makes no sound until you hear it boiling. Even then, the noise is the rush of cold vapor meeting warm air rather than the element itself. Nitrogen has mastered invisibility, allowing it to fill vast spaces unremarked. Electrical glow. Run an electric current through N2 at low pressure and it shines violet blue. That glow paints the inner glass of plasma globes and high-altitude sprites that flicker above thunderstorms. The color arises when excited electrons fall back toward the ground state, releasing photons in the near-ultraviolet and deep indigo bands. In medieval folklore, such lights were called silent lightning. Again, nitrogen working without flame. 2.2. Location in the periodic table. Visualize the periodic table as a great stone archway. Start on the left side, count 7 columns to the right, and land in group 15, once called the pnictogens. Here sit nitrogen, phosphorus, arsenic, antimony, and bismuth, an eclectic family that flips from essential to toxic as atomic weight rises. Period 2. Nitrogen occupies the second period, meaning its electrons fill only the first and second shells. This compact size bestows high electronegativity, rivaled in its period only by oxygen and fluorine. The small radius lets nitrogen's p orbitals overlap tightly, weaving the triple bond strength, valence pattern. With 5 valence electrons, nitrogen may share 3 to complete an octet, often forming 3 covalent bonds in ammonia, nitriles, or amides. In nitrates, it stretches to 4 valence bonds through coordinate sharing, holding a formal positive charge balanced by oxygen's pull. In metal nitrides, nitrogen behaves as N superscript 3, resembling oxide yet stronger in bonding to titanium, aluminium, magnesium, metals used in ceramics that withstand re-entry flames. Chemical neighborhoods. Leftward sits carbon, master of chains. Rightward, oxygen, fiery and reactive. Nitrogen mediates between them. It tempers oxygen's eagerness yet offers lone pairs that accept protons, thus bridging acids and bases. Its family trends downward show increasing metallic character, Phosphorus forms both acids and solids. Arsenic straddles. Bismuth glints like a heavy metal. Nitrogen alone remains a gas at room temperature, an airy outlier among heavier kin. 2.3. Prevalence and natural sources. Atmosphere. Earth's broad ocean of N2. Look above at any clear sky. The pale blue you see is sunlight scattered by molecules, mostly nitrogen. At sea level, each cubic meter of air holds roughly 900 grams of N2, yet you will never taste it. It is colorless and silent, but mighty in mass. The atmosphere contains about 4 quadrillion tons of nitrogen, pressing gently on every hillside, every wave, every lung. Hydrosphere, dissolved but diluted. Cold seawater can hold 30 milligrams of N2 per liter. Waves trap bubbles that provide fish with tiny reservoirs of unreactive gas, maintaining buoyancy and moderating pH. Deeper down, nitrates and ammonium circulate through plankton blooms, while vents spew ammonia plumes that feed chemosynthetic ecosystems. Lithosphere. Nitrates, ammonia ices, mineral cages. In arid deserts, sodium nitrate crusts crack into brittle plates called caliche. These deposits once fueled Chilean industry and European gunpowder. Clay minerals trap ammonium ions between silicate sheets. Permafrost stores ammonium hydrates. In volcanic fumaroles, jets of nitric oxide oxidize to yellow crusts of nitrate salts. Biosphere, cyclic dance. Every leaf, mussel, and microbial enzyme holds nitrogen in amino acids and nucleotides. Atmospheric N2 alone cannot nourish plants. Instead, symbiotic bacteria wield the enzyme nitrogenase to cleave the triple bond, splicing hydrogen pairs to form ammonia. Lightning fixes smaller amounts, fertilizing fields with dilute nitric acid that rain washes into soil. When organisms die, other microbes return nitrogen to air by stepwise denitrification. Ammonium to nitrite, nitrite to nitrate, nitrate to nitric oxide to N2O, and finally to N2. The cycle spins like a giant wheel, balanced by lightning at the top and bacteria at the base. Cosmos. Nebulae, comets, moons. Spectra of dark interstellar clouds reveal nitrous oxides and hydrogen cyanide absorbing starlight. On Pluto and Triton, nitrogen frosts sublimate into thin blue atmospheres under pale sunshine. Saturn's moon Titan boasts rivers of liquid methane beneath a haze of nitrogen gas thicker than Earth's, laced with complex nitriles that fall like orange snow. Astronomers suspect that distant exoplanets orbiting cool red dwarfs may host nitrogen atmospheres tinted purple by photochemistry unlike anything on Earth. Human industry. Synthetic abundance. In 1909, Fritz Haber and Carl Bosch tamed the triple bond with iron catalysts and 200 atmospheres of pressure, forging ammonia from N2 and hydrogen. Today, more than 180 million tons of ammonia arise annually, feeding half the planet's crops. Steel plants blanket molten metal with nitrogen to inhibit oxidation. Electronics manufacturers purge argon chambers first with dry nitrogen to remove water. Server farms breathe cold N2 gas to cool processors, while breweries flush oxygen from kegs to protect flavor. Liquid nitrogen on Earth's surface. Though rare in nature, liquid N2 streams from laboratory dewars, fogs film sets, and powers cryogenic preservation. Surgeons use it to freeze warts and precancerous cells. Chefs dunk herbs to shatter them into confetti, swirl ice cream in seconds, and crackle chocolate mousse into brittle shells. Physicists chill superconducting magnets for MRI machines. Every liter poured out surrenders 200 liters of gas, enough to blanket a small room with invisible fog. Quiet interlude. Rest for a moment and imagine yourself standing on a high plateau under starlight. Feel a soft breeze across the face. That breeze is almost entirely nitrogen. It holds you, insulates you, and yet never weighs heavy. Hear the hush. No hiss, no rustle. The giant is quiet, guarding sparks and lungs alike. Take a breath 4 counts in. Hold 4 counts. Release 6 counts. Let the steady presence of N2 sink deeper into awareness. We will soon journey outward, following nitrogen from stellar furnaces to Titan's orange skies, but first remain a heartbeat longer in this calm cushion of Earth's own atmosphere. Role in the universe. 3.1. How nitrogen is forged in stars. Imagine the earliest universe, a young darkness lit only by hydrogen and helium. The first giant stars bloom, burn, and in their hot hearts a quiet alchemy begins. Among those nuclear forges, one process stands out: the CNO cycle. Hydrogen nuclei fuse into helium with carbon, nitrogen, and oxygen acting as catalysts. Within each massive stellar core, protons slam into carbon-12, creating nitrogen-13, which beta decays to carbon-13, captures another proton, and so on until helium emerges and carbon is reborn. During the loop, nitrogen is never destroyed in aggregate. Instead, it appears in transient isotopic steps, flashing from +1 to +3 oxidation states inside a sea of plasma. When the star ages and helium fusion ignites, convection drags nitrogen-14 outward. A red supergiant surface can display it as telltale absorption lines, a spectral fingerprint that astronomers read across tens of thousands of light-years. Eventually, the star's core collapses. In a Type II supernova, shock waves blast processed layers into surrounding space. That ejected shell contains carbon, oxygen, and a generous peppering of nitrogen atoms made heavier by additional neutron captures. Supernova 63 Vela sprinkled Earth's neighborhood with 14 nucleon nitrogen 600 million years ago, a gift still measurable in deep ocean sediments. Smaller dying suns, like our future sun, puff off planetary nebulae rich in nitrogen cyanogen, painting turquoise rings that hang in telescopic silence for millennia. Yet forging is only half the tale. When interstellar gas collapses into second-generation stars, nitrogen joins dust grains composed of icy ammonia, hydrogen cyanide, and nitriles. Those chilled molecules become part of protoplanetary disks. Observatories such as ALMA track them in radio frequencies, noting how ammonia emission outlines spiral arms of newborn systems. Nitrogen therefore moves from furnace to frozen dust and back to furnace in a galactic heartbeat. Take a steady breath now. As you inhale, feel a thread of connection between the air in your lungs and a red giant 15,000 light-years away. Exhale and imagine that thread as a line of nitrogen atoms passing through nebulae, joining cosmic cycles older than the Milky Way itself. 3.2 Nitrogen's travels across galaxies and planetary worlds. Focus on a single nitrogen molecule released by a dying star. For 1,000,000 years it drifts through cold interstellar medium at 200 degrees below zero, colliding only rarely with its neighbors. Cosmic rays strike it, sometimes knocking off electrons, briefly turning it into N2, which glows faint indigo before recombining. Eventually the molecule becomes trapped in a gravitational eddy of a birthing solar system. On the outer rim of that disk, temperatures remain frigid. Nitrogen condenses with methane, carbon monoxide, and water, building crumbly comets. In our own solar system, such bodies still orbit in the Kuiper belt. When they fall sunward, solar heat liberates nitrogen gas that jets from their surfaces and sweeps dust into luminous tails. Observers in dark deserts witness those tails as pale blue arches. They breathe terrestrial nitrogen while watching cosmic nitrogen bloom. Further inward, 3 worlds dramatize nitrogen's versatility. Titan, Saturn's largest moon, holds a thick nitrogen atmosphere 4 times denser than Earth's. Methane and ethane rain across dunes, yet the bulk gas remains N2 at 98%. Titan's photochemistry fashions imines and nitriles that snow onto its surface. Some scientists wonder whether slow, cold reactions there might resemble precursors of life's early chemistry. Pluto sports bright plains of frozen nitrogen that flow like glaciers. Sputnik Planetia's surface is so cold that sublimation engraves polygons, each the size of a city. As sunlight glances across dawn, nitrogen ice grains refract a faint blush, reminding telescopes that even distant dwarf planets share elements with our breath. On Neptune's moon Triton, black geysers vent nitrogen gas propelled by seasonal heating of subsurface frost. The plumes rise 8 kilometers high, carry dark dust, then fade into supersonic winds. Spacecraft photographs show streaks of charcoal dust across pink nitrogen snowfields, a silent ballet at the edge of the sun's power. Beyond the solar system, astronomers scrutinize exoplanet atmospheres for biosignatures. Detection of nitrogen alone does not prove life, yet its presence stabilizes climates by broadening habitable temperature ranges. Models predict that Earth-sized planets around cool red dwarfs may need thicker nitrogen layers to prevent oceans from freezing under dim starlight. Conversely, too much nitrogen can push greenhouse gases into runaway steam states. Thus, nitrogen is the quiet thermostat of planetary habitability, rarely starring, always moderating. Between stars, nitrogen appears mostly in molecular form, but spectrometers also reveal ammonia and hydrogen cyanide. These molecules absorb and emit microwaves that pass through dust, making them excellent tracers of star-forming regions. In the Orion molecular cloud, astronomers map ammonia temperature gradients to study embryo stars the way a physician uses thermography. Nitrogen becomes not only building material but also a cosmic thermometer. Consider again your breathing. Somewhere far beyond the heliosphere, another nitrogen molecule begins a journey that will last 50 million years before it finds a new planet. Somewhere on Titan, a nitrogen grain just sublimated, starting its rise into a twilight sky. The element binds these quiet events together in one universal symmetry. 3.3 mysteries and future questions surrounding cosmic nitrogen. Even with radio telescopes and space probes, scientists still wrestle with nitrogen puzzles. One concerns the nitrogen isotopic ratio. Meteorites display an enrichment of nitrogen, 15 compared to Earth's atmosphere, implying fractionation processes in the primordial nebula or later solar wind implantation. Comet 67P revealed an even higher N15 signature. Did nitrogen build into planetesimals differently than oxygen and carbon, or were later outgassing and biological cycling responsible for modern ratios? The answer could rewrite models of Earth's early mantle and even the origin of our oceans. Another mystery dwells on hot Jupiter exoplanets. Observations suggest some of these giants possess ammonia at altitudes where it should be destroyed by intense ultraviolet radiation. Perhaps deep convection cells dredge ammonia upward faster than photolysis can break it. Or energetic particles from stellar winds may drive non-LT chemistry that shields ammonia bands. Future missions like the James Webb Space Telescope aim to resolve high-resolution spectra that can fingerprint nitrogen species directly. Closer to home lies the riddle of Martian nitrogen fixation. The red planet soils contain nitrates whose concentration varies with latitude and depth. Some nitrates likely formed by ancient lightning in thicker atmospheres, others by meteor shock. Yet small seasonal spikes in methane hint at active subsurface chemistry. If perchlorate brines host microbial life today, nitrogen cycling could still occur beneath dunes, echoing Earth's earliest ecosystems in slow motion. Mars sample return missions hope to test isotopic signatures that reveal biological versus abiotic pathways. Lastly, nitrogen polymer science ventures into exotic territory. Under 200 gigapascals, a polymeric cubic gauche phase of nitrogen may form, predicted to store 10 times the energy of TNT. If synthesized and stabilized at ambient pressure, such a material could power spacecraft or revolutionize safe explosives. High-pressure laboratories are racing to trap these phases before they snap back into N2. The challenge is akin to bottling lightning, binding pure nitrogen in extended chains without releasing its colossal potential prematurely. Each of these mysteries reminds us that nitrogen still keeps secrets despite its mundane presence in every breath. Its triple bond seems simple, yet within and around that bond lies a tapestry of cosmic evolution, planetary weather, biological alchemy, and future energy. Gentle closing reflection. Draw a steady breath through the nose for 4 counts. Hold 4. Release for 6. Let your shoulders soften. Picture an immense, transparent ocean of N2 overlaying the planet, spreading limb to limb, horizon to horizon. Above that blanket, auroras dance green and violet when solar winds brush nitrogen atoms. Far beyond, Pluto's nitrogen glaciers glow under starlight, and nebulae carry nitrogen ice among newborn suns. Feel the cool, silent strength of this element seep into awareness. It does not burn brightly like oxygen or glitter like carbon. Instead, it waits, watches, balances, whispers stability into every environment from vacuum to thundercloud. As we move next to nitrogen's role in living cells, carry the hush of cosmic nitrogen with you, a reminder that giants can be gentle, and silence can be the most powerful voice in the universe. Take one last easy inhale, extend the exhale, and let your thoughts drift like nitrogen atoms in interstellar twilight, unhurried, peaceful, ready to dream. Role in life. 4.1. Nitrogen in the human body. Take a gentle breath and hold it for a heartbeat. In that single draft lie billions of nitrogen molecules. Most will leave exactly as they entered, yet life would unravel without them. Roughly 3% of every person's mass is nitrogen, woven into the chemistry of consciousness, motion, healing, and memory. The amino backbone. Proteins, the workhorses of biology, are long chains of amino acids. Each amino acid wears an amine group, a pair of hydrogens bound to nitrogen that allows peptides to link in endless permutations. Myosin filaments pulling muscle, insulin shepherding glucose, antibodies patrolling blood, all rely on nitrogen's lone pair to form peptide bonds. Without that lone pair, the helixes and sheets of protein architecture would collapse, leaving a silent cell. Genetic ink. Every spiral rung of DNA carries nitrogen. Adenine, thymine, cytosine, and guanine each contain multiple nitrogen atoms arranged in aromatic rings. Those atoms lend sites for hydrogen bonding that hold complementary strands together. When a cell divides, polymerase enzymes read nitrogen patterns like Braille, copying genetic sentences base by base. A mutation often arises when a single nitrogen base changes shape, underscoring how even one atom can alter a life's trajectory. Messenger and mediator. Inside neurons, nitrogen appears as neurotransmitters. Dopamine, serotonin, glutamate, and gamma-aminobutyric acid all hinge on amine groups. When an action potential reaches a synapse, vesicles release these molecules. Their nitrogen atoms dock into receptors, triggering cascades that shape joy, focus, fear, and calm. Another small gaseous molecule, nitric oxide, diffuses directly through membranes to widen blood vessels. One exhaled whiff announces its job done. Energy currency. Adenosine triphosphate, the cell's rechargeable battery, contains nitrogen in its adenine head. When you blink or dream, ATP donates a phosphate, and nitrogen helps reassemble the molecule for the next contraction, the next thought. Without this perpetual rebuilding, muscles would lock and thoughts would flicker out. Immunity and repair. White blood cells craft nitric oxide radicals to pierce invading bacteria. Meanwhile, collagen that knits skin after a scrape relies on hydroxyproline, an amino acid whose ring contains nitrogen. During fever, the liver reroutes amino nitrogen into acute phase proteins that ferry iron away from pathogens. The element becomes both sword and shield, attacker and architect. Waste management. Proteins eventually break down, releasing ammonia. Because ammonia is toxic, the liver converts it into urea by stitching two nitrogen atoms to a carbonyl. Blood carries the urea to kidneys, which filter it into urine. This elegant cycle keeps pH steady and prevents nervous system injury. Evolution in fish, reptiles, birds, and mammals adjusted the pathway, but every variant depends on nitrogen to ferry excess back to soil and sea. Medical partnership. Surgeons harness liquid nitrogen to freeze warts, cataract lenses, and precancerous skin, halting cellular metabolism within seconds. Anesthetists mix nitrous oxide with oxygen to ease pain. Hematologists label amino acids with nitrogen. 15 to trace hidden bleeding. Everywhere, the element serves quietly, never demanding stage lights, always present. Pause now. Feel lungs half full of air. Know that within the bloodstream amino groups are swapping partners. DNA bases are zipping, nitric oxide is murmuring to arteries, and ammonia is slipping into the urea cycle. Each second the body rewrites itself with nitrogen ink. 4.2. Nitrogen across the wider biosphere. Shift your attention outward. Visualize a plain of knee-high grasses waving under summer wind. The green color owes itself to chlorophyll, a pigment whose ring framework embeds 4 nitrogen atoms around a magnesium heart. Without that tetrapyrrole, photosynthesis would stall, and oxygen would dwindle. Nitrogen sits at the center of the planet's breathing, fixing the triple bond. Most organisms cannot use atmospheric N2. It's bond too strong. Instead, specialized microbes wield the enzyme nitrogenase, a protein complex shimmering with iron and molybdenum clusters. The enzyme captures N2, batters it with electrons, and outputs ammonia. The cost is steep: 16 molecules of ATP for each N2 broken. Yet the reward is life. Legume root nodules glow pink from leg hemoglobin, delivering oxygen at just low enough levels for nitrogenase to function. Wheat fields rely on cyanobacteria in soils, rice paddies on free-living anabaena, tropical forests on symbionts tucked inside leaf litter. Every continent hosts invisible artisans converting sky to soil. Nitrification and denitrification. Once ammonia enters Earth, other microbes oxidize it to nitrite, then nitrate. Plants sip nitrate through roots, build amino acids, feed herbivores, and the chain climbs. When organisms die, decomposers return fixed nitrogen to oxidized forms. In oxygen-poor wetlands, denitrifiers finish the circuit, reducing nitrates back to nitrous oxide or N2. A single nitrogen atom may tumble through this will tens of thousands of times over geological ages. Life at extremes. Deep-sea vents teem with archaea that oxidize ammonia, creating energy gradients in eternal midnight. Polar lichens scrape nitrate from snow. Desert cyanobacteria draw atmospheric ammonia through crusts baked at 50 degrees Celsius. On the high Andes, flamingos feast on algae whose pink pigment contains nitrogen rings similar to heme. Even in dry Antarctic valleys, microbes survive on nitrate salts blown from ancient seas. Nitrogen and climate. Nitrous oxide is a greenhouse gas 300 times stronger than carbon dioxide per molecule. Wet farming, thawing permafrost, and fertilizer runoff all elevate its levels. Conversely, increasing plant nitrogen uptake can store more carbon in biomass, moderating warming. The balance hinges on microbial genes spread through soil like invisible circuitry. Climate models now embed nitrogen feedbacks, revealing that green policies must manage not only carbon but also this silent element. Human intervention. The Haber-Bosch process, invented in the early 20th century, feeds roughly 4 billion people each year. Ammonia factories pull hydrogen from natural gas and nitrogen from air under iron catalysts at 200 atmospheres. The resulting fertilizer doubled grain yields. Yet excess nitrates leach into rivers, fueling algal blooms that rob waters of oxygen, creating dead zones. Agroecologists promote crop rotations with legumes, precision fertilizing, and biochar amendments to close the loop more gently. Plant defenses and colors. Alkaloids such as caffeine, nicotine, morphine, and quinine owe their punch to nitrogenous rings. They repel insects, lure pollinators, or soothe fever. Flavonoids color petals and fruits, guiding bees and birds. Chlorophyll's breakdown in autumn frees nitrogen, which trees pull back into roots just before leaves fall, painting forests gold and crimson. Interstellar seeds. Meteorites deliver amino acids laced with nitrogen, hinting that prebiotic chemistry is universal. Laboratories simulate early Earth lightning over methane, ammonia atmospheres, producing glycine, alanine, and adenine. These sparks write a preliminary alphabet from which evolutionary poems emerge. If life exists beneath Europa's ice or in Titan's methane lakes, its alphabet will almost certainly include nitrogen pages. Pause once more. Inhale slowly for 4 counts. Hold for 4. Exhale for 6. Picture an unseen thread linking your breath to a bean root nodule, a coral polyp, a snow algae bloom, and a microbial mat curling inside a geyser. Nitrogen moves through all of them, carrying information and energy, marrying sky to soil, heat to ice. Quiet closing of the block. Nitrogen's role in life is neither dramatic nor flamboyant. It operates as builder, messenger, electrician, and recycler, seldom demanding applause. It paints chlorophyll green, DNA blue-black, and the auroras fringe violet. It whispers through synapses, stitches muscles, and ferries waste away. It feeds wheat that becomes bread and poplar roots that hold riverbanks. Let that quiet competence settle into your own rhythm. Breathe in calm air. Feel nitrogen flow through alveoli into blood past beating heart. Know that some of those atoms will soon become part of enzymes repairing tiny tears in muscle, or neurotransmitters scripting dream stories. Know too that after fulfilling their task they will drift back to the sky, ready to join another season of growth far away. In our next block we will explore how humanity harnesses this giant, from cryogenic surgery and fertilizer to rocket fuel and nitrogen lasers. But for now, rest in the knowledge that every creature on Earth, from hummingbird to whale, from moss to maple, thrives because nitrogen stands quietly in the background, turning planetary breath into biological architecture. Take one final soft inhale. Hold. Let go. Feel gratitude ride outward on that exhale, carried by the silent giant who neither boasts nor fades, who simply continues, cycle after cycle, life after life. Practical applications. 5.1. Medicine and human health. Picture a quiet hospital corridor at dawn. Fluorescent lights hum softly, infusion pumps tick, and somewhere a nurse wheels a silver dewar that trails wisps of white vapor. The vapor is liquid nitrogen changing to gas, a transformation that underpins dozens of therapies. Cryosurgery. When dermatologists treat warts or early skin cancers, they dip a cotton-tipped probe into liquid nitrogen cooled to -196 degrees Celsius. Touched to living tissue. The probe freezes intracellular water so rapidly that ice spikes pierce membranes, halting metabolism in seconds. A gentle hiss rises, a bloom of frost forms, and unhealthy cells surrender without scalpel or bleeding. Ophthalmologists remove cataract-clouded lenses the same way, creating a tiny nitrogen ice bond that grips the opaque lens for safe extraction. Cryopreservation. Banks of eggs, sperm, stem cells, and umbilical cord blood stand in tall metal canisters surrounded by liquid nitrogen. At -196 degrees Celsius biological time slows to near zero. Cell membranes glassify. Enzymatic reactions pause. DNA damage nearly stops. Parents facing chemotherapy store fertility for future hope. And research labs preserve genetic lines of endangered corals or alpine plants. When thawed carefully, viability often exceeds 90%, testimony to nitrogen's gentle stewardship. Anesthesia and analgesia. In operating theaters, anesthetists mix nitrous oxide with oxygen. Colloquially called laughing gas, N2O crosses the lung-blood barrier quickly, binding to opioid receptors and releasing dopamine for brief euphoria. Then sedation. Dental clinics rely on it to ease patient anxiety. Neonatologists use calibrated doses to relieve pain in premature infants whose fragile systems cannot tolerate opiates. Respiratory support. Pressurized cylinders labeled medical nitrogen deliver dry, oil-free gas to purge anesthesia circuits, power pneumatic drills in neurosurgery, and provide an inert carrier for inhaled nitric oxide therapy. In neonatal intensive care units, nitric oxide gas streams at parts per million levels through ventilators, relaxing pulmonary arteries in newborns with life-threatening hypertension. Nitrogen here acts not as drug but as vehicle, delivering the messenger molecule safely to alveoli. Diagnostic tracers. Nuclear medicine teams synthesize N13 ammonia in cyclotrons. Its short 10-minute half-life makes it ideal for positron emission tomography of cardiac perfusion. Chemists also substitute N15 into amino acids to study protein turnover in metabolic disorders, tracing labeled nitrogen as it moves from bloodstream to muscle, liver, and urine. Because N15 is stable, patients receive no radioactive dose, yet clinicians glean precise data on nutrition and disease. Medical device manufacture. Catheters, stents, and surgical sutures must reach sterility without melting. Gamma radiation and ethylene oxide gas sterilize some supplies, but heat-sensitive devices ride on cold nitrogen plasma. In vacuum chambers, an electric field strips electrons from N2, creating reactive species that puncture bacterial cell walls while leaving plastics intact. Pause and breathe in slowly. Behind every crisp exhale, millions of silent nitrogen molecules carry away excess heat, excess moisture, and with them, the tiny anxieties that cling in clinical halls. 5.2. Technology and heavy industry. Leave the hospital and walk toward a field of towering steel columns and pipes. A petrochemical plant, a semiconductor fab, a wind turbine blade workshop. They all rely on nitrogen's inert calm. Haber-Bosch synthesis. More than 180 million tons of ammonia arise each year from nitrogen and hydrogen at 350 degrees Celsius and 200 atmospheres over iron catalysts. That ammonia feeds half of global crop yield, becomes nitric acid for rocket oxidizer, and fuses with carbon to form urea for diesel exhaust scrubbing. Each time bread rises in a village bakery, Haber-Bosch lingers invisibly within the wheat. Shielding and purging. In steel mills, molten metal contacts an atmosphere of nitrogen to suppress scaling. Welders blanket stainless steel joints with flowing N2 that drives away reactive oxygen. Winemakers sparge barrels with food-grade nitrogen to displace oxygen that would brown Chardonnay. Photographic film factories once pumped darkrooms full of N2 to halt moisture and dust. Modern microchip fabs still do, using 99.99% pure gas to keep wafers atomically clean. Electronics cooling. Data centers pulse with heat from densely packed processors. Some halls route chilled nitrogen gas through floor ducts. Others immerse boards in dielectric liquids that boil, then condense in rooftop heat exchangers, creating a closed nitrogen-based loop. Quantum computers' qubit chips sink into baths of liquid helium cooled further by evaporating liquid nitrogen, the latter acting as silent pre-coolant. Laser technology. Nitrogen lasers, simple yet powerful, produce intense ultraviolet pulses at 337 nanometers. Archaeologists use them for delicate stone artifact cleaning. Atmospheric physicists fire them upward to probe aerosols by fluorescence. Coupled with dye lasers, nitrogen flash lamps pump medical photodynamic therapy systems that destroy tumors under targeted light. Metallurgy and materials. Titanium and aluminium react with nitrogen at high temperatures to form hard nitrides. Tool steels receive a surface nitride layer, nitriding, that improves wear resistance beyond chrome plating. In powder bed 3D printers, a sealed nitrogen atmosphere prevents oxidation as lasers sinter stainless granules into aerospace brackets. Carbon-nitrogen alloys called cermets cut through engine blocks without losing edge. Energy storage and transport. Cryogenic tanks of liquid nitrogen serve as safe energy sinks. When off-peak wind farms generate excess electricity, they power air liquefaction plants. Stored cold nitrogen is later warmed to drive turbines during evening demand, a system named liquid air energy storage. Unlike lithium batteries, the feedstock is atmospheric and inexhaustible. Spaceflight. Rockets vent nitrogen gas to pressurize propellant tanks, purge lines, and spin-start turbopumps. The James Webb Space Telescope sailed into orbit within a cocoon of dry, high-purity nitrogen to protect delicate gold mirrors from moisture and dust during assembly. Mars rovers carry compressed nitrogen in their sample return caches to prevent Earth microbes from contaminating regolith tubes. Soft exhale now. Think of nitrogen as the backstage technician of industry. Never taking a bow, always ensuring the spotlight stays steady. 5.3. Everyday life and familiar comforts. Step out of the factory and into daily rhythms. Nitrogen follows quietly. Food and drink. Open a bag of crisps. The satisfying puff is 99% nitrogen, inserted to keep chips fresh by blocking oxygen and moisture. Draft stout beers pour through nitrogenated taps that create velvety microbubbles and a creamy head. Chef's Whirl cream siphons charged with N2O cartridges, foaming lemon curd or rapid infusing basil into olive oil. Instant freeze dessert parlors dunk strawberries in liquid nitrogen, shattering them into airy shards that melt sweetly on the tongue. Tires and sports equipment. Aircraft and Formula One teams inflate tires with dry nitrogen to stabilize pressure across temperature swings. Cyclists use small nitrogen cartridges to reseat tubeless tires trailside. Tennis ball cans hiss open, releasing pressurized nitrogen that kept felt bouncy since factory sealing. Lighting and displays. Compact fluorescent bulbs contain a drop of mercury vapor inside a nitrogen-argon buffer. LED chips age more slowly when encapsulated in nitrogen-purged resin. High-definition OLED panels are manufactured in glove boxes flushed with nitrogen to prevent oxygen quenching. Home safety. Fire suppression systems in telecommunication closets release tanks of pure nitrogen. The oxygen level in the room drops below 14%, extinguishing flame without water damage. Portable canisters of compressed N2 power nail guns, airbrushes, and inflatable life vests. Gardens and soil. Granular fertilizers deliver nitrate or urea to lawns and crops. Backyard compost piles rely on the carbon-to-nitrogen ratio. Too many autumn leaves stall decomposition, but kitchen vegetable scraps rich in nitrogenous proteins restart microbial heat. Gardeners sense nitrogen's presence in deep leaf green and swift stem growth. Air travel. Every commercial aircraft wing holds dewars of nitrogen-enriched air that flood fuel tanks, reducing oxygen concentration and preventing vapor ignition. Cabin fire decker units push nitrogen to smother potential flames. Even the oxygen masks passengers drop in emergencies are part of chemical generators that release oxygen while discarding hot nitrogen to keep temperature stable. Leisure and entertainment. Stage magicians pour liquid nitrogen into silver bowls to conjure clouds that spill across footlights. Haunted houses pump chilled nitrogen fog for eerie low-lying mist. Science museums mesmerize children by shattering flowers or rubber balls after a dip in frigid N2. Pause one last time. Breathe in through the nose. Feel taste buds anticipate crisp packaged snacks, bicycle tires gripping asphalt, garden beans stretching leafy arms. Breathe out. Sense nitrogen departing, ready to cushion another moment somewhere else. Quiet closing of the block. From hospital ward to launch pad, from barley stout to quantum chip, nitrogen serves with patient versatility. It can flash blue in a laser pulse, whisper cold over surgical steel, or lie dormant in a snack pouch. No applause follows, yet without its inert calm flames would rage, food would stale, circuits would corrode, and lives would falter. Allow gratitude to settle on this silent giant. Inhale 4 counts. Hold 4. Exhale 6. Imagine nitrogen flowing out to steady welders' arcs, chill ice cream churners, and lift balloons toward stratospheric experiments. Beyond every sparkled moment lies an invisible lattice of N2, quietly upholding technology, flavor, safety, and health. When you next see a knob frost over a clinic doer, a crispy chip keep its snap, or a data center purr contentedly, think of nitrogen's cool, colorless presence. It turns fragility into resilience without asking the limelight, content to remain backstage while the world moves forward. Curiosities and Mysteries. 6.1. Fascinating and surprising facts. Diamond rain on Neptune begins with nitrogen. High-pressure simulations show that methane deep inside ice giant mantles splits into elemental carbon and hydrogen. Yet methane arrives there only after nitrogen, carbon, and hydrogen combine in interstellar clouds. Each methane molecule carries a memory of ammonia that once drifted beside it. When diamond nuclei descend through blue storms, the lost partner nitrogen lingers as cyanide ions in swirling seas, painting Neptune's infrared spectrum with faint chemical signatures. The coldest temperature ever recorded in a laboratory relies on liquid nitrogen. Physicists at Massachusetts Institute of Technology once pre-cooled atoms with liquid nitrogen before laser techniques drove them to 500 picokelvin, half a billionth of a degree above absolute zero. Without nitrogen's first chilling step, lasers alone would miss that record by orders of magnitude. At such temperatures, atoms move slower than a garden snail crossing the width of a proton. Laughing gas was once Victorian party entertainment. In the early 1800s, itinerant chemist Humphrey Davy filled silk balloons with nitrous oxide during private soirees. London socialites inhaled the gas, collapsed into unbridled laughter, then penned whimsical diary entries describing mind pleasantness. Decades later, dentists discovered its analgesic gift. What began as parlor amusement became a cornerstone of modern anesthesia. Blue flashes in thunderstorms come from nitrogen laser action. 1 out of every 100 lightning bolts triggers a fleeting ultraviolet pulse called a gigantic jet. During the microsecond that follows, excited N2 ions radiate at 390 nanometers, the same wavelength as laboratory nitrogen lasers. Spectrographs catch the glow as a blue spike, proving that nature invented gas phase lasing long before humans glass-sealed electrodes. Neon signs sometimes contain nitrogen, not neon. Bright purple storefront tubing labeled neon often holds low-pressure nitrogen that yields a violet band under alternating current. Genuine neon glows red-orange. Sign makers choose nitrogen for lavender accents because it costs less and lasts longer. Next time you stroll an evening avenue and see violet letters suspended in glass, you may be reading silent nitrogen poetry. The taste of packaged coffee depends on a nitrogen flush. Fresh roasted beans release carbon dioxide that would bloat sealed bags. Manufacturers flush the bag with high-purity N2. Insert a one-way valve and seal. O2 escapes slowly while oxygen remains near zero, preserving aromatic oils. Open a bag and inhale notes of cocoa, cedar, or citrus, preserved courtesy of the quiet giant. Pause and breathe. Inhale 4 counts, hold 4, exhale 6. Notice how even small facts about nitrogen carry vast spans of temperature, color, pleasure, and flavor. 6.2. Unresolved mysteries and unusual phenomena. Why does Earth's atmosphere hold a constant 78% nitrogen? Geochemists model volcanic outgassing, subduction recycling, and biological fixation, yet precise feedbacks that stabilize the ratio remain hazy. Too little nitrogen would shrink atmospheric pressure, boiling oceans at lower temperatures. Too much would thicken the sky, trapping greenhouse gases. Planetary scientists seek to learn whether tectonics, biology, or impact erosion set the thermostat. The missing nitrogen in the solar nebula. Meteorites from the early solar system exhibit a puzzling deficit of nitrogen compared with predictions from interstellar cloud chemistry. Some researchers blame ultraviolet photolysis that selectively drove N2 outward. Others propose adsorption onto icy grains that later evaporated beyond Jupiter. Sample return missions to comets and the metal-rich asteroid Psyche aim to weigh this hidden reservoir. Unknown nitrogen chemistry in Titan's upper haze. Cassini's mass spectrometer detected high-mass negative ions above Titan that defy known nitrogen-carbon chemistry. The ions reach thousands of atomic units, forming a brownish aerosol that rains organic snow on methane dunes. Laboratory discharge chambers have yet to replicate the exact molecular soup. Solving the puzzle could hint at prebiotic pathways unique to cold nitrogen atmospheres. Nitrogen's role in Martian methane spikes. The Curiosity rover measures seasonal pulses of methane. Some hypotheses involve ultraviolet breakdown of nitrates releasing oxidants that then react with buried organics, freeing methane. Until scientists sample subsurface ice or return drilled cores, nitrogen's link to Martian methane remains an open whisper beneath the red dust. Polymeric nitrogen, the ultimate green explosive. Computational models predict a cubic gauche phase where each nitrogen bonds to 4 neighbors, storing 10 kilojoules per gram. Synthesized briefly at high pressure, the phase reverted to N2 within picoseconds after decompression. Researchers pursue clathrate frameworks or carbon-nitrogen scaffolds that might stabilize this energy crystal at ambient pressure. If unlocked, cubic nitrogen would deliver rocket impulse with only harmless N2 exhaust. Nitrogen fixation on early Earth. Before nitrogenase evolved, lightning and meteor shocks likely supplied ammonia. Yet isotopic evidence in 3-billion-year-old shales hints at biological fractionation well before cyanobacteria. Some theories propose mineral catalysts at hydrothermal vents converting N2 to ammonium using iron-sulfur clusters, a geologic prototype of the enzyme. Field studies at modern black smokers sample fluids for similar abiotic ammonium. Pause again. Exhale tension. Feel curiosity settle like a feather on still water. Nitrogen invites wonder precisely because it hides its drama behind calm bonds. 6.3 Little-known anecdotes and historical vignettes. Blue milk and the Sydney Show. In 1932, Australian dairy chemist Norman Coleman bubbled nitrogen dioxide through milk, oxidizing carotene and bleaching casein. The milk turned pastel blue. Crowds at the Royal Easter Show queued to taste lunar milk, expecting blueberry flavor, yet found ordinary creaminess. Newspaper photographs led to urban legend that astronauts would drink blue milk on future moon missions. The Nitrates War of the Pacific. During 1879, the Atacama Desert saltpeter beds provoked conflict between Chile, Bolivia, and Peru. Nitrate export duties, crucial to European gunpowder, swung alliances. When the war ended in 1884, Chile controlled the world's largest nitrogen market until synthetic Haber fertilizer dethroned natural nitrate. Today ghost towns sit under blazing skies, walls still dusted white with sodium nitrate crystals. The accidental discovery of aniline dye. In 1856, William Perkin attempted to synthesize quinine from coal tar nitriles. His flask yielded a sticky black sludge. Washing with ethanol revealed a vivid purple solution. The dye, mauveine, revolutionized textiles, coloring royal gowns and impressionist canvases. Nitrogen rings in that molecule marked the dawn of synthetic organic chemistry. Canned air for the Eiffel Tower. When Gustave Eiffel erected his tower for the 1889 exposition, engineers feared rust in the riveted beams. They piped dry compressed nitrogen through hollow sections to push out humid Paris air during construction. Inspectors in the 21st century found interior surfaces still smooth, sealed under a century of passive nitrogen armor. The soda fountain race. Early 20th century pharmacists charged tonic water with hand-pumped nitrogen bubbles, creating smoother fizz than carbon dioxide. Soda bar owners painted storefront signs bragging of N2 cream sodas. The craze faded when industrial carbon dioxide became cheaper, yet vintage recipes persist among craft beverage makers who prize nitrogen's velvety mouthfeel. Nitrogen thrusters on the Hubble Space Telescope. When astronauts serviced Hubble in 1999, they carried small handheld units called safer packs filled with compressed nitrogen gas. If a tether snapped, astronauts could pulse nitrogen jets to return to the shuttle bay. The system was tested but never used in emergency, yet each mission rehearsed its hiss, trusting silent gas to guard explorers amid bright cold vacuum. The butter-soft dive of freediver Herbert Nitsch. To avoid nitrogen narcosis at 400 meters, He inhaled a hypoxic mix and slid downward, switching to pure oxygen only after ascending partway. He still absorbed massive nitrogen, experiencing hallucinations likened to liquid dreams. His record stands, cautionary and awestruck, underscoring nitrogen's narcotic caress under crushing pressure. Quiet closing reflection. Take an easy breath in 4 counts. Hold. Exhale slowly for 6, letting any buzzing curiosity fade into gentle wonder. Nitrogen may appear plain, yet behind its colorless veil lie diamond storms, violet bolts, blue milk, and cubic crystals of stored thunder. It has shaped wars, inspired dyes, preserved genomes, and illuminated planets lit by far suns. As you ready for deeper rest, imagine a single nitrogen atom leaving a decaying star, drifting eons through black quiet, landing in a cloud droplet, falling onto leaf litter, rising into a soybean root, joining an amino acid, crossing a dinner table, slipping into your bloodstream, and finally continuing outward on your next exhale. The journey never ends. The silent giant keeps moving, balancing, creating, surprising. Feel the bed beneath you steady as the invisible nitrogen sea pressing gently on the roof. The trees, the dreaming city. Allow that sea to carry you now, weightless, supported, moving toward the hush of sleep where the most curious mysteries become tranquil stories of light and color. Inhale soft stability. Exhale calm inquiry. And let nitrogen's endless patience cradle the night. Elemental dreams and sleep descent. 7.1. Gathering quiet images of nitrogen. Settle a little deeper into whatever cradles you. Notice how the mattress, sofa, or patch of cool grass seems to rise and meet your body from below. That upward presence mirrors the gentle pressure of the atmosphere. 10 tons of air resting on every square meter of Earth, yet you feel almost nothing. The reason is nitrogen. It spreads the weight so evenly that the body interprets it as a hug rather than a burden. Close your eyes or soften the gaze. Picture a vast night sky stretching beyond the ceiling, a dome of deep velvet blue. Within that dome tiny motes drift, each no larger than 2 bonded atoms. They move in silence, colliding, rebounding, exchanging kinetic whispers too faint for the ear. Those motes are nitrogen molecules, so numerous that counting them all would require more time than the universe has existed. Let the first image form, a gauzy indigo wave. It rolls overhead in slow motion, a ribbon of air visible only because your mind has chosen to paint it. Each crest is a pulse of nitrogen, each trough a place where oxygen and argon rest. The wave's forward motion is steady yet unhurried, perfectly suited to the approaching calm. Watch it pass and feel the chest follow its rhythm. Rise, pause, fall. 4 counts in, 4 counts held, 6 counts out. Now the dome darkens. Stars brighten as if someone dimmed the world's lanterns. A faint jade-green curtain curls across the north horizon, an aurora born in nitrogen ions. Each ripple is a burst of electromagnetic energy translated into light. The curtain lifts, folds, then dissolves, leaving a hush as complete as a cathedral long after the choir has left. Shift to a second image. A dandelion seed floating on the night breeze. The seed tumbles and pirouettes, its parachute of filaments catching pockets of N2 that push it higher, farther, until it settles on soft soil yards away. Every summer meadow depends on this dance. Seeds riding nitrogen currents that carry life from hill to valley. A final image glimmers faintly. A silver doer standing in a laboratory alcove. Frost coats the neck, shimmering under a single desk lamp. From the open mouth white vapor spills, curls downward, and pools at the floor like flowing silk. That vapor is nitrogen gas warming from its liquid sleep, rising only when it has surrendered its chill. The scene is cold yet comforting, the cold of refreshment, not of peril. Let these 3 scenes, indigo wave, jade curtain, silver doer, merge in your imagination. They weave a tapestry of motion and stillness, color and transparency. Nitrogen is all of them at once. Sky, ocean, cosmic glow, gentle frost. Notice the body again. Shoulders rest lower than a few minutes ago. Jaw hangs loose, releasing even the memory of clenching. Hands fall palms up or palms in, whichever feels effortless. Inhalation is quieter now. An inlet stream feeding a tranquil lake. 7.2. Weaving nitrogen into the rhythm of sleep. Begin a simple inner mantra, one that travels on breath without forcing any sound. Inhale, calm air. Exhale, quiet night. Each time you take a breath, let those two words pass in the mind. They need no volume, no emphasis, only presence. Calm air, quiet night. The cadence matches the 4/4/6 rhythm effortlessly. As the mantra settles, imagine nitrogen molecules as tiny lanterns, soft spheres glowing cool blue. With every inhale, lanterns enter and drift through branching airways until they reach millions of alveoli. There they hand off their modest gifts: pressure to keep lungs inflated, micro-whispers that soothe pulmonary tissue. Most lanterns then turn around and depart on the exhale, still bright, still calm. They exit into the room and join a silent choir of blue lights hovering just above the floor. See if you can sense those lanterns inside the chest, cool but not cold, bright but not glaring. They bob gently on every expansion of the rib cage, then float away as muscles release. In moments they will rise through curtains or slip beneath doors, joining the broader ocean of night air. Now broaden the focus beyond the lungs. Move awareness to the bloodstream. Picture erythrocytes gliding along capillaries, ferrying oxygen and carbon dioxide, passing clusters of nitrogen lanterns that simply observe, offering softness rather than chemistry. Even here nitrogen plays role of silent buffer, preventing gas partial pressures from swinging too sharply, guarding each cell against violent swelling or collapse. Shift again, this time to the brain. Envision synapses in twilight, neurons dimming their chatter as adenosine levels rise. Inside vesicles wait molecules like serotonin and GABA, each carrying an amine group, each containing nitrogen. As a neuron fires its last volleys of the day, nitrogen lines up to hush impulses, to tip the seesaw from alertness toward sleep. Return to the mantra. Calm air on inhale, quiet night on exhale. The words may feel slower now. Let them float at whatever pace breathing has chosen. Travel outward once more beyond the body. Imagine stepping onto a high plateau under starlight. The sky above is a transparent sea of nitrogen. It stretches from the soles of your feet to the border of space 50 kilometers up. Each breath you take dips into that sea. Each exhale returns a ripple. In the far distance a thundercloud flickers, forging nitric oxide with silent electric fingers. Light travels, yet the hush remains unbroken. Feel a breeze slide over skin. The air temperature matches body temperature so closely you barely detect movement, only a hint of N2 molecules brushing vellus hairs. That brush carries away 1 or 2 joules of heat, just enough to cool the mind, to loosen the final threads of tension knitting forehead and temples. 7.3. Drifting into nitrogen's endless cycle of rest. Picture a great wheel turning in slow motion. Its rim is the global nitrogen cycle. Atmospheric N2, microbial ammonia, plant proteins, animal tissues, decomposer nitrates, then back to N2. Yet the wheel does not grind or clank. It turns like the second hand of some cosmic pocket watch, ticking once every century for soil, every decade for leaves, every minute for blood. In the center of this will you rest, perfectly balanced. Allow individual thoughts, a lingering task, a random memory, to become tiny paper leaves landing on the wheel's rim. At first they cling, but the wheel turns smoothly. Leaves slip into the flow, dissolve, and vanish into the vastness of nitrogen's cycle. No effort required. The element simply carries them away. Now let time itself feel fluid. Seconds elongate like honey drizzled from a spoon. Minutes melt. The usual scaffolding of clocks fades behind a curtain of blue stillness. Each breath seems to arrive sooner and leave later, as if inhalation and exhalation overlap slightly, erasing the line that separates them. Draw attention to the points where the body meets bedding. Gravity feels softer, almost optional. This sensation mirrors how nitrogen tempers pressure in deep-sea dives. Divers rely on it to prevent lungs from collapsing under water's weight. Tonight, nitrogen does the same for your thoughts, cushioning them against gravity of daily concerns. Begin a mental countdown from 8 to 0, synchronized with breaths. Inhale 8, calm air. Exhale, quiet night. Inhale 7. Exhale, quiet night. Continue downward. By the time you reach 0, let numbers dissolve altogether, replaced by the simple awareness of slow breathing. At that point, any attempt to track counts becomes unnecessary. Breathing will proceed on its own, guided by the medulla, an ancient brainstem rhythm older than language. If stray wakefulness sparks, perhaps a fresh idea or sudden sound, imagine dipping that spark into a pool of liquid nitrogen. Hear a faint hiss as it cools instantly, shrinks, and solidifies into a harmless bead that rolls away across smooth ice and out of sight. Visualize one final scene. A silver balloon rises into the night sky. It is filled not with helium but with nitrogen, lifted by heated air inside its envelope. The flame has been extinguished. Residual warmth carries the craft upward in near silence. You are in the basket, wrapped in a wool blanket. Below, city lights wane. Above, the aurora's green arch has reappeared, though softer, slower. The balloon drifts, suspended in an ocean of calm gas. Stars wheel overhead in patient orbits. Weight slips away. Thoughts loosen anchor. Even heartbeat seems to lighten, each contraction slower, more spacious. The repetitive mantra evaporates, leaving only a subtle echo, a muscle memory in the diaphragm. Sleep approaches like dawn fog, not as darkness but as a silvery mist that dims outlines, merges colors, hushes distance. Nitrogen welcomes the fog, mixes with it, becomes its carrier. The element that once watched from silence now escorts you to deeper quiet. Take one last conscious inhale. Cool, steady, uncomplicated. Hold briefly. Release. As exhalation ends, allow eyelids to rest fully. Muscles below eyes soften, cheeks sink, tongue lies flat. Breathing continues without guidance, a seamless negotiation between body and nitrogen-rich air. Let dreams form from leftover lanterns, each blue sphere a seed of narrative. Floating seeds, auroral curtains, dandelion fields, silver balloons. They will arrange themselves into gentle stories while the conscious mind slumbers. The silent giant stands guard, pressing lightly from every direction, holding warmth in, holding noise out. Night expands. The body drifts. Nitrogen carries you into sleep's wide ocean, steady and sure. Now, as our journey softly comes to a close, allow yourself a moment of quiet reflection. Feel how each calm breath gently connects you to the element we've explored tonight, one tiny piece in the infinite mosaic of the universe. As you drift gently toward rest, picture your thoughts like atoms of the element we've visited today, floating serenely through the vastness of your imagination. Just as elements combine, transform, and quietly support all life around us, your mind now settles, combining peace with tranquility. Remember how every atom within you once journeyed through stars, oceans, and forests, cycling endlessly through the great natural symphony. Tonight's element, in its silent and humble way, is part of that eternal flow, gently sustaining the heartbeat of existence itself. Think of the wonder we share. This quiet exploration, this peaceful communion with matter. With each soft exhalation, you return the element back into the embrace of the world around you, an invisible yet profound exchange. You are part of this endless rhythm, connected in every silent moment, every restful sigh. Imagine the element we've discovered tonight, existing beyond time, beyond human stories, gently present long before us, and quietly continuing long after. It carries the memory of ancient worlds and dreams of futures yet unseen. You too hold this gentle eternity within each breath. Allow yourself now to float gently, as if carried by the element's invisible hands, toward restful sleep. Feel comforted by knowing that the universe generously shares every atom, every molecule, every peaceful moment with you. Let your eyelids grow heavy, your thoughts softly dissolve like mist at dawn. Know deeply that you belong, gently cradled in the elemental harmony of the cosmos. May your dreams tonight be filled with quiet wonder and peaceful exploration. Rest now, knowing you are safe, cherished, and connected to this gentle element, to this gentle earth, and to the vast, beautiful silence of the universe itself. Good night, and rest peacefully, embraced by the elemental calm of night chemistry.